Hello, and welcome to an episode of ES Repair. I am your host, Mr. Fix-It. If you've seen my previous video, I discussed about bipolar transistors, both the NPN and PNP transistors. In this video, I'm going to be discussing about field effect transistors. First, we're going to be talking about the JFET, or Junction, field effect transistor. Then we'll be talking about the MOSFETs, which are the metal-oxide semiconductor field effect transistors. Third, we'll discuss about the unijunction transistor. And finally, we'll be discussing about the programmable unijunction transistor. So let's get started. Here we're looking at junction field effect transistors, also known as JFET. Now there are two kinds. You have the N channel and the P channel. The current will flow from the drain to the source and from the source to the drain. They're not real picky about which direction the current flows. Now they can be used from amplifications, mostly like preamplifiers, and they are also used to generate high frequencies. Now the way these work is, as you apply a small current, I mean very, very small, you can control what current flows through the transistor. Now these are not like bipolar transistors, because bipolar transistors rely on current, whereas field effect transistors rely on voltage. They have like the advantages over the current controlled bipolars, and the reason for this is because the input, which is the gate, the resistance between the gate and the channel is so high that there's no effect whatsoever by connecting these directly to the output of an integrated circuit, such as the 555 or a 4017. You know, any integrated circuit can connect directly to one of these without any effect. Now what happens is the resistance can be so high it acts almost like a diode. Now if you've ever tested a diode, you can see that when you apply the voltage to the diode, it will show you how much voltage it requires. Well, the resistance is so high on these things that it acts kind of like a diode. Now they can be damaged just like a bipolar. But next, let me show you how these things work. Here is a basic setup to test your JFET. Now I'm going to be using an M meter or an amp meter. Now if you look to the left, you'll see how I got my batteries connected. It does create 18 volts, but I'm going to use the center, as you see there, where the 0 between the two batteries. This will create my common ground or a neutral ground. This will allow me to generate a negative 9 volts, as you can see in the picture. The P channels connect the exact same way. It's just the difference is that the gate function is the opposite of the N channel, which I'm going to demonstrate. But this is a quick look at the setup. You get the 300 ohm, that's my current load. The 1 kilo ohm will limit the current to the gate. So let's get started. Here I have a demonstration set up to show how these transistors work. And what we're going to do is, I've got the 330 ohm resistor. This is going to be my load current. I've got the 1K, which I haven't unhooked because I'm going to show you how sensitive these transistors are. First thing you want to do is, before you test your transistor, you want to get all the pins on the transistor touching each other, just like I'm doing here in this one row. These transistors are voltage controlled, and they do store a charge, so to speak. Unlike bipolar transistors, they depend on current. The more current you apply to the base, the more current you can control between the collector and the emitter. These are different. These are voltage controlled. The more voltage that you give it, the more current you can control with it. But these are voltage dependent. Now here I've got the charge removed. I'm going to insert it into my board. You want to be sure not to touch any of the pins, because these transistors are sensitive. Let me insert it into the board. Now the way this is going to work, I've got my two 9-volt batteries, and as you've seen in my diagram, I wanted to give you a clue how this was all going to connect and work. Now I can connect my power supply. Turn my voltmeter on. This meter here will measure the current, and this meter will measure the voltage at the gate. Now, to give you an idea about the power supply, I do have this lead here connected to the neutral, or the ground, which is this one right here. As you can see, there's 0 volts, so I'm on the ground. Now if I test this up here, you can see I get 9 volts, positive 9 volts. Now if I touch the yellow one down here at the bottom, you'll notice it says negative 9 volts. Now, these voltages are in respect to this ground. And by seeing the diagram, you'll see how I managed to get my positive 9 volts and negative 9 volts. This resistor here, which is a variable resistor, will control the voltage. If it goes this way, the gate will become more positive. If it goes this way, it'll become more negative. Now, depletion refers to the state of the transistor. Think of it as an open switch. Either the switch is normally open, which means that you have to press the button in order for it to conduct electricity, or normally closed switches means that you have to push the button to disconnect the power, interrupt the current going through the switch. Well, these are considered normally closed transistors. Here, I'll demonstrate. Let me turn my meter to milliamps. Now, notice I have no connection to my base. This is to my gate. What this does is to demonstrate that the transistor is normally closed, meaning that it's going to normally conduct current without the gate. Now, in order to turn off this transistor, it must have a negative voltage. Now, for the P channels, it's the opposite. To turn them off, you have to give it a positive voltage. Now, the P channels will connect the same way as this does. The only difference is the voltage. Here, this is an N channel, which means it requires a negative voltage to turn them off. P channels require a positive voltage to turn them off. Now, notice I've got positive 9 here, negative 9 here. Okay, so now that's ready. Now, because the transistor is still conducting, watch what happens when I touch the gate. Now, I'm just going to touch the gate with my finger. Now, watch what happens. Did you notice how it went dead? Just from touching it with my finger, the transistor was turned off. This is how sensitive these transistors are. Now watch what happens as the negative charge dissipates in the transistor. Notice how the current is slowly increasing? This is because the negative charge is dissipating in the gate. And it'll keep going until the charge disappears. As you see here. Now, watch again. All I'm doing is just touching the gate with my finger, and I can turn the transistor off. Now, let me connect my 1K resistor Now, the way these work, there's no polarity to these, actually. I can have the current go through the drain to the source, or from the source to the drain. These aren't that real picky. The gate can either have a positive voltage or a negative voltage, so it can work either way. Now, notice here, let me get my adapter connected. Notice here, I'm going to hook this positive to this positive lead for the base. Now, notice here it says that I have negative 0.66 volts. Just under 1 volt. Here, it went from 7 milliamps down to 4 milliamps. So you can see how the negative voltage affects these transistors. Now, let me change it some more. And watch the voltage as I do this. Now I can go all the way up to 15 here. That'll be close enough. Now look, I've got 0.7 volts at the base. This is positive because you notice there's no negative symbol. Now I'm pulling 15 milliamps. Now you can see how sensitive these transistors are. Now what's going to happen here now, let me turn it the other direction. See how it keeps going up? Okay, well, let's make it more negative. Now notice how the voltage drops, the current through the transistor also drops. This is how they're voltage dependent. Everything is controlled by voltage at the gate. Now I'm going to get this down to 0. And there you go. I've completely turned off the gate. And I'm only using negative 2.68 volts. And now the transistor's turned off. Now if I was to remove the negative charge, notice the current's turning, the transistor turned back on. Now if I apply the negative charge, these can be used as switches amplifiers. This is how sensitive these transistors are. Just like that, just by removing the negative voltage. Well, this is how a demonstration of how these things work. Now, let's move on to how to test these transistors to see if they're good. Now, here is a very simple test you can do. This meter here has diode checking capabilities, and this is what you're going to need. Now, you can test the resistance, but you won't be able to get a very accurate reading because the way these transistors are set up. But first, let's check the ohms. I'm going to show you what you could check. Here I have my ohm meter turned on. It's over the limit. Now, I'm going to take my test leads, test them to show you the resistance in the meter, that the meter is working. Next thing we're going to do is, according to the data sheet, this pin here, which is my center pin, is the source pin. This pin on the end is the drain pin. And this is the gate pin. Now, you can use the ohm meter to test between the drain and the source, like this. Now, you will receive, some resistance, not much. It's rather low resistance. This one here is just less than 200 ohms. Now, to show you that these can work in either direction, the resistance will vary slightly. Here, let me switch the polarities of the ohm meter. Oop, there we go. So as you can see, they vary just slightly. Now that is one indication that it's working. Another indication is turn the ohm meter or your digital meter to diode checking. This gives you enough voltage to test the gate. This is what we're going to do, is test the gate. Now if you put your positive lead to the gate, your negative lead to the drain, you'll notice that it takes 0.724 volts. Okay, that's an indication that it works. Same thing if you want to check your source. You should also get around 0.7 volts. So far it checks out. Now, let's check in reverse polarity. Put my negative on the gate, put my positive on the drain. You should get a very high resistance, just like I'm showing here. It's over the limit. Okay, let's check the source pin. Again, you should get an over the limit or no measurement whatsoever. This is a good indication that this transistor is functioning. Now, two things to keep in mind. If you get the same thing, which is OL, regardless of how it's tested, like this. Now see, this shows it works, but let's assume that it don't. Now if you get this resistance, no resistance whatsoever, in either polarity that you're checking, this indicates that the gate is open, which means that the transistor is bad. Now if you're getting something like this, and either polarity checking the gate, this would mean that the transistor is shorted, and in other words, it's faulty. And this is the best, simplest way to test a junction field effect transistor. Now you can do the same thing with the P-channel transistors, but again, you should only be conducting in one direction only when you test these diodes, using a diode jack, as I demonstrated here. Well, this is how you test the junction field effect transistor. Now, let's show you how to test a MOSFET. Here we have metal-oxide field effect transistor, also known as MOSFET. Now, those of you who have been working on your amplifiers and things like that, you've probably came across these. I've had people writing into me asking about how do you test these. So, here you are. Now, we're going to talk about two different modes. We're going to talk about the depletion mode and the enhancement mode, as you see here. The depletion mode means that the transistor is conducting current between the drain and the source by default. In other words, you have to apply voltage to the gate to turn them off. Enhancement mode is the opposite. By default, no current flows between the drain and the source. You must apply a voltage to the gate to turn them on. Now they are available in two different types, the N channel and the P channel. We'll be working with an enhancement mode N channel MOSFET known as the IRF 510. Now these are similar to JFETs, but they're also different. JFETs had a connection between the gate and the channel, whereas the metal oxide field effect transistors have a very thin film or layer, which is kind of like a glass layer of silicon oxide or metal oxide between the gate and the channel, and it insulates it. Now, because of this very thin layer, these transistors are very vulnerable to static electricity. Now, I will show you later in this video as we move on how sensitive these things are to static electricity. Now, these things are very useful because the current is very little. We're talking about microamps or nanoamps. So these transistors can be connected directly to the integrated circuit without any effect whatsoever. And these pretty much have an infinite resistance between the gate and the channel. Now you can use these either as a switch, or you can use these as a voltage controlled variable resistor. And believe it or not, these can be used in amplifiers. Now you also have power MOSFETs, which can handle a lot of current. And I'm going to show you one in a few moments. Now you'll see that the MOSFETs can switch very high currents because they have such a low on-state resistance, and I'll show you that too. So first we're going to get the transistor connected. My first pin is my gate, the second pin is the drain, and the third pin is my source. Now the current will go from the drain to the source. Now be careful because some of these transistors do have a diode in reverse bias. This is to protect the transistor from inductive loads such as those created by motors. So you want to make sure that you replace them exactly. So let's get started. Here I have my board set up to demonstrate the MOSFET transistor. Now, as you can see, there's no resistor. This makes them really good to use when high current is in demand, because there is no current that goes to the gate, only voltage. And it requires no more current than what an integrated circuit can provide. So this makes them really, really useful for direct connections to integrated circuits, such as a 555 timer chip. Now, you'll notice there's no resistors. I've got this red wire standing up because I'm going to demonstrate something shortly. I've got my power supply hooked up. I've got my alligator clips going to my light bulb right here. Now, as you can see in its current state that the transistor is turned off because my light bulb's not glowing. These transistors, this one specifically, is an N-channel MOSFET. That means that this transistor requires a charge to turn it on. This is known as enhancement mode. Depletion mode refers to the transistor is already on, but needs a charge to turn it off. Now, for the N-channel enhancement MOSFETs, you require a positive charge to turn the transistor on. Now, these transistors are so sensitive that in order to work with these, you've got to have an anti-static wrist strap to help discharge any sort of static buildup that you may create. And as you can see, the alligator clip here is connected to the ground to dissipate any static electrical charge that I may produce. Now, let me show you what happens and show you how sensitive these transistors are. I'm going to remove my ground, and I can touch the wire just with my finger. And see, I can turn the transistor on. This means that I'm having enough static buildup to turn the transistor on. Now, if I was to hook that back up the ground, I don't have that problem. Man, I could just sit here and rub the floor and still touch it. Nothing happens. I can't turn it on. But if I remove it and I can build up electricity, static electricity, look what happens. The gate turns on. This is the thing about static electricity you have to be careful with, because it can destroy the MOSFET. So let me turn that back on, connect that back to my ground. Now, notice the light bulb is still on. The reason for that is because since these transistors use a metal-oxide film to insulate the gate from the channel, it creates a sort of capacitance. And this capacitance, like capacitors, will store charge. And depending on how much charge there is in the gate, it can take a while for the charge to dissipate. Well, all you have to do on this transistor is ground out the gate like that. And now the transistor is turned off. Now, because I got my wrist strap still grounded, I can go back and touch it and rub the carpet and nothing will happen. This is the best way to protect these. So if you're going to be working and testing with this MOSFET, be sure you got a anti-static wrist strap connected to a ground. to help dissipate any kind of static charge you may have, especially if you're going to replace these. If you, after this test, and you find you have a faulty MOSFET, when you install the new one, you still need to take the precautions to avoid static electrical buildup. Now, another thing that these transistors are good for is switching. They have all kinds of switching capabilities. These things can switch from off state to on state and vice versa within 8 billionth of 1 second. That is very, very fast. That's faster than a blink of an eye. Now I'm going to add this 330 ohm resistor to the gate. This is the only thing the resistor is used for, as I will demonstrate. Let me plug in my red wire again to the gate. Now, remember when you touch the red wire to the positive? See what happens? If you touch the positive, the light comes on. But as soon as you remove it, this resistor discharges the charge out of the gate, forcing the gate to turn back off, or turning the transistor back off. This is what the resistors are used for. They only dissipate the charge that's built up in the transistor, so the transistor can turn off. Now, another thing that you can use these transistors for is amplification. Not only can these transistors be used in switching due to their very high speed switch capabilities, they can also be used in amplifications. I'm going to hook up this variable resistor and show you how you can control the voltage. Now, these are mostly used for high-speed switching, such as those in power supplies. Well, I'm going to show you how these can also work in amplifications. Now, you can control the voltage. If I was to turn the voltage in one direction, hold that in place. See, I can make the light come on. Now if I turn it the other way, I can actually control how much current goes through the transistor. I can have a little bit of current go through, or I can increase the current to go through. Back and forth. Now it requires very, very, very little current. We're talking about nanoamps to microamps because of the gates not directly connected to the channel. I can do it linearly or linear. And that's how these can be used as amplifiers. Now I'm going to show you the resistance when these transistors turn on. Now this is the reason why these transistors are highly used in amplifiers and switching power supplies. Now as you can see, the transistor is currently off. I have my test meter zeroed to remove the resistance that runs through the probes. So when I turn this on, watch the resistance. Notice how low it's going? Not even an ohm. Now, because the transistor is in its on state, let me plug that back in. You'll notice how low this resistance goes. We're talking about a half of 1 ohm. This is why they are highly used for high-speed switching, because these transistors can handle a lot more current than a bipolar transistor can. Plus, this allows them to produce less heat. The less the resistance, the less heat that is produced when their current is flowing through the transistor. And this is pretty much how these transistors work. And you can use these methods to test the MOSFET to ensure that it's completely working. Here we have the junction field effect transistor. Now, this really isn't a true transistor or anything like that. It behaves more like a thyristor than it does a field effect transistor. These are mostly voltage controlled switches, is basically all they are. When the emitter's voltage reaches the threshold, it switches on, conducting current from the emitter to base 1. And that's all it does. I mean, they have no amplification or nothing. All these are is basically just a voltage controlled switch. Now, they will remain on until the current falls below the hold current, at which time the transistor will turn off. Now, these aren't as commonly used today as they were, say, 10-15 years ago. They're primarily used in pulse and timing circuits, sensing circuits, thyristor triggers, etc. They're all but extinct right now. But let me show you how if you come across one of these, or you're going to use this in one of your hobbies, let me show you how you can test these and show you how you can hook them up to test in different ways. Here we have a basic test, just using an ohm meter. Now, any shorts or large differences in readings will indicate that it's a bad transistor. Now, with this one, you're basically just measuring the resistance between base 1 and base 2. Now, they should be the same in both directions, and they will measure, a few kilo ohms or more, and they should be pretty much the same in either direction or polarity if you switch your probes around. Now, this doesn't necessarily mean that the transistor works or that it's good, so let me show you another way that you can test to see if the transistor is working. Here we have a simple basic timing circuit. Basically, that's what this is. The 100K and the capacitor is what's called an RC timing circuit. The resistor will slowly charge the capacitor. When the emitter reaches a certain threshold, then it conducts and discharges through the transistor. Now, this should create somewhere around 1 kilohertz. And of course, it's not exact. I'm just kind of guessing. And just hook it up to speakers or a frequency counter or an amplifier or something, and this will give you an idea if the transistor is working like it should. And the 100 ohm resistor is basically just a current limiter to help control the transistor. I'm not sure exactly what it's for, but in all the circuits that I've used, it was always there. So I couldn't tell you exactly what it's for. because these switches are only working between the emitter and the base 1. So I'm not sure what it's for. Now, next we have the programmable junction. And this here, if when you see the symbol for it, if you're familiar with silicon controlled rectifiers, which is a thiostor transistor, doesn't this look similarly to it? The only difference between this and a SCR is that the gate is on the cathode side instead of the anode side. That's the only difference. Basically, it's the same thing. Now, what this sets the unijunction transistor apart is it requires a voltage divider. Now, as for the unijunction, it had a fixed threshold for the emitter. And when the voltage reached that threshold, then it would conduct. Well, the programmable, you can program the gate to a certain voltage. When the anode becomes more positive than the gate, then the transistor turns on, and then the current flows through the anode to the cathode. And that's basically how these things work. You can adjust the gate. It's like a dam. The taller you build a dam, the more the water has to build up to get over the dam. This is the same thing. Now, these two were also used in the same things as pulse and timing circuits and sensing and all that, even pulse shaping. That's what these were used for. But you don't see these very often. I haven't seen these things in years. Now, to test a programmable unijunction transistor, you can use either an ohm meter or you can use a diode check. Now, if you're going to use an ohm meter, as you can see in my illustration, you put the positive probe to the anode and the negative probe to the cathode. There should be no conduction or open circuit between the anode and the cathode. This is with no connection to the gate, as you see here. Now, you can briefly connect the gate to the cathode, and it may turn on the transistor, creating a low resistance between the anode and the cathode. Now, this won't work with all meters. It just depends if they can provide enough power. If we're going to use a diode check, the measurement between the anode and the gate with no connection to the cathode should be as low, similar to that of the silicone diode. If you've tested those, they usually run about 0.5 to 0.7 volts. And it should only do this in only one direction. If you diode check between the gate and the cathode with no connection to the anode, you should have no conduction in either direction. And that's how you can test the programmable unijunctions. As for testing a circuit, you can use this to demonstrate whether or not your transistor is working. You'll need a 100k ohm resistor and a 0.01 microfarad capacitor. You could do this with a 9-volt battery. If you look to the right, you'll notice the two 1K resistors. This creates the voltage divider and sets the threshold to the gate. So when the capacitor is charged to the threshold of the gate, then the gate transistor turns on and it opens the circuit to where the capacitor drains through the transistor. Now you can hook these up to a speaker or frequency counter, amplifier, etc. And you should hear a tone right around 1 kilohertz. And this is a good way to test to see if the transistor is functioning or not. Well, this concludes this video. I apologize if it seems very long, but I wanted to ensure that I include as much detail as I could about these transistors. But be sure to vote you like or dislike the video. If you have any questions, feel free to ask. I am your host, Mr. Fix-It. Thank you for watching.